Hello everyone, my name is Dr. Hemlata. Welcome to my channel. In this video, I will be showing you how to find the various probabilities of binomial distribution using R and how it behaves with varying values of the parameters. And we already know that binomial distribution describes the number of success in a fixed number of independent Bernoulli trials, and each trial has only two possible outcomes, either success or failure. So it has two parameters, that is one first is n, that number of trials, and p, the probability of success, that is fixed in each trial. So in theoretical context it has only two parameters. Now here we will be dealing with the software R. So I'll show you one by one like how it works and how to find out the various probabilities. We will understand this with the help of the example. Since we are dealing with the binomial distribution, we have to install a package. To generate the data of binomial distribution, we will be using R binom function. So if you want to know what is R binom, you can put the question mark and write R binom and then press Ctrl Enter. It will take you to the help here in right hand side corner. If you see what is this R binom, so it works under stats package. It comes under binomial distribution, and this is the function given here, R binom. It has three arguments, n, size and p. And what are these n, size and p? Here it is described in detail, right? N is the number of observations. If length n is greater than 1, the length is taken to be the number required. Size is number of trials. Number of trials, it can be 0 or more. Then probability of success in each trial, right? So we'll put all these parameters one by one. Okay. Now first we will install the package, stats package. So for that we will go to the tools and then install, and then here we'll be writing as stats. Okay, then we will install it. Since I have already installed it, so I'm not going to install it again, but you have to do it like this. After installing the package, you have to use the library function like this to load the package, to load this package. Okay, after loading the package, we can easily work in the this R binom function. Now we will be understanding the problems with the help of example. So we'll take case wise. So case 1, we are trying to understand what happens to the binomial distribution if the experiment is repeated a large number of times. Okay, so we will try to understand, if we repeat the experiment a large number of times, how it behaves, the distribution behaves. Okay, so for initially we will take n. N is what is n? N is the number of times the experiment is repeated. Okay, for example, if you are tossing a coin, then how many times you are tossing a coin? Okay, this, if you tossed a coin 10 times, and this you did at once, 10 times you tossed a coin, we will take it as a one experiment. So experiment is a collection of trials. Okay, so one experiment is a collection of trials. So here we are doing 20 experiments, so we will get 10 up to 20 times we will be doing the experiment. Okay, so here we did the experiment 20 times. That means what? We will be getting the output 20 times, right? And what output we will be getting? The generated values of x. X is what? X is the number of successes. So if you repeat your if you do one experiment and if you are repeating it, here it is written size. Size is number of trials in each experiment. So if you are repeating a coin 10 times, this is your one experiment, then how many times we got a success? Suppose out of 10 we got a success 3 times we got a success, 7 times we got failure. So we will be getting our first, the value of the output will be 3. Similarly, we will repeat our experiment again second time. Second time again we will toss a coin 10 times, and in that 10 times suppose we got now success maybe 8 success and 2 failure, then the second value of the output will be 8. Likewise we will be getting the output. And what is the probability of success? Here we are assuming it is 50-50, right? 0.5. There are equal chances of getting failure or success in each trial. Okay, so it is fixed in each trial, that is 0.5. Now since we are generating the data, randomly generating the data using R binom, we are using that set.seed function. It is generally used to fix the randomly generated values, because again and again if we generate the random data, it will provide us new different values. So to avoid this, what we want throughout the result, throughout the analysis, we want the same number of randomly generated values, right? So we will fix that value using set.seed. So this is the number 1 2. So for this particular 1 2, whatever function I am running, it will work for that. So you can give this any number 1 2 or 1 2 3 or any number whichever you want. So for that particular number, the function will be generating the fixed number of values. Okay, now let us generate the values. So we are using R binom function, and it needs 3 arguments. N is the number of times the experiment is repeated. So we will repeat our experiment 20 times. Here we have assigned the value n is equal to 20. Size, in each experiment how many trials we want, that is size. So 10 trials we want for the time being, and p is the probability of success. And we are storing this output in the random numbers. That means we will be getting 20 random numbers. Here we have already written 20 times we are repeating the experiment. Okay, so 20 random numbers we will be getting. So now let us run this. We'll run one by one by pressing the control enter, and then we will see these are the my randomly generated values of x. These are the number of successes. Okay, first time if we repeated the experiment, we did the experiment, we repeated the trial 10 times, we tossed a coin 10 times, we got 3 successes. Okay, second time if you did an experiment and you did 10 trials under that, and you got 6 successes. Likewise you did the experiment 20 times. Okay, so this is the number of successes in each experiment. Okay, now since these are the repeated values, see 5 is coming many times, 6 is coming, so we can make a frequency table. You know how to make the frequency table? That can be done using table function, table, and then we want the frequency table of random numbers. Okay, then we will see for how many times the values were repeated. 1 came 1 time, 2 came 2 times, 3 4 5 6 came 4 times, 7 came 1 time, right? So this is the frequency table. We can plot this frequency table, right? We can make a histogram of this. So we will use hist function, and then we are making histogram of random numbers. We can give the color, what type of color we want of the histogram, what border will be white, and then title, main title of the histogram. This is the x-axis title, this is the y-axis title. So it is a simple function we can do. Okay, now if we run this, we will see here what type of histogram it is. Okay, so this is how it looks like. That means what? So if a number of trials, if you go to the theoretical aspect and if you find what was the mean, the average value, average number of times the success comes, so n into p, n is the number of trials, p is the probability of success. So here number of trials are 10. Here if you see number of trials are 10, p is the probability of success. So what is the probability here? If we run this, 5. Okay, so if you again go to the diagram and see, p is equal to 5. Here it is lying. Okay, so from the nature of the distribution, you can see it is negatively skewed, like most of the values are lying below the mean is 5, right? and less values are more than 10, more than 5, right? So it is negatively skewed. But now here we want to know, if we increase the number of trials, if we increase number of times the experiments, okay, what will happen? So first we did 20 times. Now suppose I increase it 200 times, 20 to 200, okay, what will happen? So I run the same thing, everything I'm keeping same, only I'm repeating the experiment 200 times. So now what will happen to the distribution? Okay, we'll see, I repeated it 200 times, mean was still 5. So what, here it is 5, okay. So what I noticed is it has started taking the shape of bell shaped, right? Here and here you can see, but still little deviation is there, little skewed is there left side, okay. But it has started taking the shape of bell shaped, okay, becoming symmetric, right? So if you further increase the number of number of experiment, maybe 2000 time, or I will take it little, maybe 1000, okay. So what will happen to this? So I will repeat the same thing again, number of trials and probability is same, and I repeat my experiment 1000 time, okay. Now let us see, p is still this much, and this is now more looks symmetric, more concentrated towards mean, okay. uh, looks more symmetric, normally distributed, right? If we can further little, if we increase it 10,000, okay, let us see whether it is fully has become by normally distributed, okay. Now let us plot this and see the diagram. This is how it looks like, okay. Since we are plotting the histogram and this is a discrete distribution, so that's why it is giving the values in bar, okay. But see, you just have to see the behavior, how it is becoming. So it has fully become normally distributed, right, and symmetric, right? This is the bar for mean. So the 50% of the values are lying below, or you can say the lower than mean, or the higher than mean. So it is fully normally distributed. So what can be conclude from this? As the experiment is repeated a large number of times, the binomial distribution tends to become more symmetric and concentrated about mean, okay. So this is what we can conclude, as we are increasing the number of experiments, okay. The trials and the probability is fixed, okay. Now we will see, if we fix the experiment and if we increase the trials, okay, what will happen? So initially we had taken n is equal to 20, experiments are 20, size, the trials in each experiment is 10, probability is 5, and we had already seen what was the distribution. We can see it again just to remember, okay. And we'll see how the plot was, okay. So now here this was the plot, and mean was, when trial was 10, p is 0.5, the mean was 5. So it was skewed, and the distribution was not normal, not good, right? Skewed distribution. So now we are slowly increasing the trials in each experiment. So we took 10, it was skewed, and mean was 5. Now we, let's say, take it 100, experiments are 20, we are increasing the number of trial in each experiment, and now let us run this again and see the distribution, okay. uh, Now we can see what is the mean if the trials are 100 and the probability is 0.5. Here I have written, so mean is 50, np, right, n into p. So if you do this, so 50, see, you can say 50, mean is lying somewhere here, and is now still it is not symmetric, but it has become right skewed. But you can see most of the data is lying between 45 and 55, right? So maybe plus minus 5 of the mean, right? So it has, as I am increasing the number of trials in the experiment, it is the data is very much close to the mean, right? the outcome is become more certain, right? So if I do this maybe 1,000 time, and if I see what will happen, see, let us run this and we'll see. And first let us see what is the mean. So 1,000 into 0.5, here I have written, so 500 is the mean. 500 times we are getting the average value of the success. So if I see the diagram, you can see 500 is here. So most of the values are very close to mean, or and they are lying between 480 to 520. Okay, between 480 to, so 20, the difference in the output, whatever output if you get in the next trial, you will be getting the difference between 20. It can be more or less 20, okay, but it will be close to 500. So a rough idea you have already got. You can just guess the output, and you can give your conclusions, okay. Let us little more increase it, okay. From 1,000 we are making it 10,000, and then we will see what will happen to the distribution. I'm running everything again, and this time what is the mean? Let us run this, and mean is 5,000, okay. Average number of successes will be 5,000, okay. So let us see the diagram. So 5,000, okay, mean is here 5,000, and now your output has become very much close to mean. So there is a difference of 50, right? Plus 50 and minus 50, 4 950 to 550, right? So the output has become very close to mean, that is 5,000, and there is a difference of 50 observations only, right? So the outcome is become more and more certain, right? It is very close to mean. If you know the mean, you can roughly say the outcome is going to be this much if you repeat the number of trials or increase the number of trials, okay. So what can we conclude from this? As the number of trials increases, the binomial distributions become more concentrated around its mean and reflecting greater certainty in the outcome, and that is what we have seen in the diagram. The outcome has become more certain. It is very close to 500, that 5,000, that is the mean, right? So that is how we can have an idea, and we can understand what happens to the binomial distribution if we repeat the experiment large number of time, or if we increase the number of trial in the experiment, okay. Now further we can take case number 3. Here we can find out the probabilities for the given value of x. X is the number of successes, right, in the experiment. So let us take the example. Here I have written the example, and to find out the probability for the given value of x, we use d binom function. D for density, right? So density means it will give us the probability. So d binom, we will be using this. If you want to know the details about d binom, you can put this help question mark and d binom, okay. Again it will take you to the help here right hand side, and you see what all arguments are needed for this d binom here, okay. Log, here log is the new term. If you want your probability in terms of log, then you put it, but we don't want generally it, okay. So it is by default false, so we will keep it false, okay. Now let us take the example. uh, a pilot survey, assume a situation. It's a pilot survey. Let us say we did a survey, and we assumed a situation that where out of a group of 20 people, 8 of them wear glasses, okay. So out of 20 there were 8 people those who were wearing the specs. This is the pilot survey was done before doing the study, okay. The original study. So from this we got an idea what will be the probability if we probability of the people wearing the glass in that particular population, okay. So using this information, we want to know what is the probability of getting 3 people who wear glasses out of a sample of 10, okay. So now we will use this prior information to find out the probability, and we will fix the parameter values, okay. So we will define the parameters. So p is the very much required information, probability of getting success, and that is given 8 out of 20 people wear the glass. So probability is going to be 0.4, right? 8 by 20 is 0.4. So this is the probability of success, proportion of people wearing glasses in the population is 0.4. So 40% of the people wear the glasses in that particular population. This is what already we know. Now suppose we took a sample of size 10, we selected 10 people randomly from that particular population. So n is going to be 10. We are denoting the argument is size here for D binom. So we have fixed it as size is equal to 10. But the meaning of this is we selected 10 people from that population where 40 people on an average are wearing the glasses. Okay, now we want to know the probability that what is the probability that 3 people will be wearing the glass out of a sample of 10. So we will write x is equal to 3. Okay, so this is the question, calculate the probability when x is equal to 3. So we will do this using D binom function. Okay, we will use D binom and the arguments x is equal to 3, size sample size 10, and the probability that is 0.4. We have already fixed here. Okay, assigned here. Now we will run this. So first we will run this, what all arguments are needed for the D binom, and then we will run D binom. Okay, so here the probability is saved in probability and we will print the probability. So there are 21%. This is the probability that 3 people wear glass out of 10 is the probability is 0.21. 21% chances are there. Okay, this is how we can find out the probability for the given value of x. Now we can find out the probability for the series of values of x. Okay, for each value of x we can find the probability. Okay, so the question is to calculate the probabilities for each value of x, and we can plot them also. Okay, so what all possible values of x can be? X is counting the number of people wearing the glasses. So maximum number of the sample size is 10. So maximum people who can wear the glass is 10. Minimum is, it can be 0 also. So the x can take value from 0 to 10, and 10 we have already saved, we have assigned into the size. Okay, size is equal to 10. Here you can see. Now the x can take values from 0 to 10. So we have made a sequence 0 colon 10, size. Okay, and we have assigned this value into the x values. Okay, now we can use the same function D binom and we will use everything same, only instead of one value of x we are taking a series of values of x. Okay, everything we will do the same thing, and then we can, here we will run this first, otherwise it will take the previous values. Then we will see the probabilities for each value of x. This is the probability when x is equal to 0. Probability when no person wears specs in the sample of size 10. This is the probability when one person found to be wearing the specs. When 2 people wearing the specs, 3 people, 4, like that. The probability when 10 people wear the specs. Okay, so here you can see 1 2 3 4 5. So the 5 people wearing the specs probability is maximum. After that it started reducing. Okay, now we can plot all these probabilities, how the distribution looks like. Okay, the density plot of the binomial distribution. So we will use plot function for that. We are plotting x values on x-axis and the respective probabilities on y-axis, and then this is one of the argument of plot function, what type of plot we want. So we want line diagram. Okay, we will put L, here LWD, the width of the line. So if this number you can give, if you increase this number the line will become more thick, if you decrease this number line will become thin. It depends on you how much you want. So we can make it 4 also. Okay, main, it is the title of the diagram, the density plot, and this is the x-axis title, this is the y-axis title. X-axis we are taking number of people wearing the glasses, y-axis the probabilities. Okay, now we can run this plot and we can see the diagram how it looks like. We can also add the grid lines to this diagram just to make little clear idea what is the probability assigned to each value of the x. Okay, here it is, we can see the diagram. Okay, so this is the diagram looks like. See, the probability when no person wears the specs is very 0 0 something, right? Here this much. And what we had seen is the probability when x is equal to 4. Okay, this is the maximum when x is equal to 4. The 4 number of people wearing the specs in a sample of size 10 is maximum, that is 0.25. Then it has started reducing. Okay, this is how. And earlier we have seen if the number of trials are less, it is little skewed. So here we can see it is skewed, little skewed, right? Skewed, right? But if you increase your sample, it will become more normal, right? Symmetric. That we are not going to do. We have already seen this thing. Now the another way of finding the probability is we can find out the cumulative probabilities. So there is another function in R, that is p binom, okay, to find out the cumulative probabilities. For example, the question is find out the cumulative probability of observing 3 or fewer successes. Successes mean people who wear the glasses, okay, out of a sample of size 10. So that means we need to find the probability when x is less than equal to 3. So we need to use p binom function. Here x is 3, so it will give us the cumulative probability when x can be 0 or 1 or can 2 or 3. So 0 plus 1 plus 2 plus 3. Cumulative probability we are going to get using p binom. If we put x is equal to 3, size is the trial size, 10, probability whatever we had already assigned 8 by 20, okay, and lower dot tail is equal to true. That means what? It is going to give us the lower values, means less than kind of values, so less than 3. Okay, by default also it is true, but I just gave it just to show you. This is one of the argument in the p binom function. So if you run this, it will give us the probability. Here we can plot this probability, cumulative probability. So this is the probability that 3 or less number of people wear the glass is 38%. Okay, if you want to cross check, you can just add these probabilities, individual probabilities we have already obtained. So x is equal to 0, x is equal to 1, 2 and 3. So it will add up all these probabilities, okay, and then you will get the answer 0.38. Now similarly, by using the same function p binom, we can find out the probability when x is greater than something. Okay, so just to make it little easy, I have taken calculate the cumulative probability of observing more than 8 successes, like more than 8 people wear a glass in a sample of size 10. So we are interested in finding the probability when x is greater than 8. So the greater than 8 means it can take 9 or 10. Okay, so we have to use p binom, x is equal to 8 and everything will be same. Here we have taken lower dot tail is equal to false. That means it will take higher or more probability. Okay, 8 or more, sorry, not 8, more than 8. Okay, so if we use this, we will get the probability, that is 0.0016. Okay, so this is the probability of 9 plus when x is equal to 10. Okay, so probability when x is equal to 9, x is equal to 10, if you add them you will get the same answer, like this. Okay, this is how we can do. One more function is also there where we can find out the value of x if we know the probability. Okay, so for example, if you already know, we have already obtained the probability when x is less than equal to 3, and the probability when x was less than equal to 3 was here we have where we have somewhere, this is the probability when x is less than equal to 3. So for if you know this probability and you want to know what will be the value of x, okay, then you can find out that also using q binom function. So q binom function is the quantile function of the binomial distribution. It calculates the value of x such that the probability of observing x or fewer successes in a fixed number of independent trials is equal to some specific probability. Okay, so this will give us the value of x or cumulative probability. Generally we are giving this cumulative probability and it will provide us the value of x or less than that. Okay, so the question is For example, we want to find out the number of people wearing glasses such that the probability of observing that number or fewer people wearing glasses out of a sample of 10 is equal to the specific probability. Let's say p is equal to 0.38. Okay, this answer we already know, that's why we are giving this. Okay, and this is the probability when x is equal to 0 plus 1 plus 2 plus 3. Okay, so this is the cumulative probability. Now if you use q binomial function, and here we are giving the cumulative probability, it will give us in return x will be 3. Okay, so we are going to get x is equal to 3 answer. Okay, so if you assign the cumulative probability and you use the q binomial function, instead of x you are giving the probability and it will give us the answer as x, the number x. So this means we have obtained the probability when x will take 3 or less than 3 uh, is going to be this we already know. We wanted to know what will be the value of x, so we used q binomial function. This is how we can do. So that is how we can obtain the various probabilities using software R for the binomial distribution. And we also got to know how the binomial distribution behaves if we increase the number of trials and the number of successes in the experiments, number of experiments. Sorry, so this is how we got to know from this video how to find out the various probabilities of binomial distribution using R. And also we learned how the binomial distribution behaves if we increase the number of trials in the experiment, or if we increase the experiments itself, uh, how it behaves. Okay, that we have seen. So this is how we can do the binomial distribution using software R. Uh, if you liked this video, please uh, like my video and share my video, subscribe my channel. Thank you for watching.